Hi everyone, welcome back to this video series on Bitcoin and cryptocurrency. Serialization of signatures DER. Let's look at the transaction Alice created again. In the transaction input, there is an unlocking script that contains the following DER encoded signature from Alice's wallet. So I'm not going to read all this big number here, but this is the output. That signature is a serialized byte stream of the R and S values produced by Alice's wallet to prove she owns the private key authorized to spend that output. The serialization format consists of 9 elements as follows: 0x30 indicating the start of a DER sequence, 0x45 the length of the sequence 69 bits, 0x02 the integer value follows, 0x21 the length of the integer 32 bytes, 00884D142D86652A 3F47BA 474EC719BBFB D040A570B 1DECCBB6498C 75C4AE24CB 0x02 another integer follows, 0x20 the length of the integer 32 bytes, S4B9F039FF08DF09CBE9F6A DDAC960 298CAD530 A863EAF 5393923609DB8F6E3813, a suffix 0x01 indicating the type of hash used, SIGHASH all, verifying the signature. To verify the signature, one must have the signature R and S, the serialized transaction, and the public key that corresponds to the private key used to create the signature. Essentially, verification of a signature means only the owner of the private key that generated this public key could have produced this signature on this transaction. The signature verification algorithm takes the message, a hash of the transaction or parts of it, the singer's public key and the signature R and S values, and returns true if the signature is valid for this message and public key. Signature hash types, SIGHASH. Digital signatures are applied to messages, which is the case of Bitcoin, are the transactions themselves. The signature implies a commitment by the signer to specific transaction data. In the simplest form, the signature applies to the entire transaction, thereby committing all the inputs, outputs, and other transaction fields. However, a signature can commit to only a subset of the data in a transaction, which is useful for a number of scenarios, as we'll see in this section. Bitcoin signatures have a way of indicating which part of a transaction's data is included in the hash signed by the private key using a SIGHASH flag. The SIGHASH flag is a single byte that is appended to the signature. Every signature has a SIGHASH flag, and the flag can be different from input to input. A transaction with 3 signed inputs may have 3 signatures with different SIGHASH flags, each signature signing committing different parts of the transaction. Remember, each input may contain a signature in its unlocking script. As a result, a transaction that contains several inputs may have signatures with different SIGHASH flags that commit different parts of the transaction in each of the inputs. Note also that Bitcoin transactions may contain inputs from different owners which may sign only one input in a partially constructed and invalid transaction, collaboration with others to gather all the necessary signatures to make a valid transaction. Many of the SIGHASH flag types only make sense if you think of multiple participants collaborating outside the Bitcoin network and updating a partially signed transaction. There are 3 SIGHASH flags, all non and single, as shown in Table 6.3. Table 6.3 SIGHASH types and their meanings. All 0x01 signature applies to all inputs and outputs. Non 0x02 signature applies to all inputs, none of the outputs. Single 0x03 signature applies to all inputs but only the one output with the same index number as the assigned input. In addition, there is a modifier flag SIGHASH ANYONECANPAY, which can be combined with each of the preceding flags. When ANYONECANPAY is set, only one input is signed, leaving the rest and their sequence numbers open for modification. The ANYONECANPAY has the value 0x80 and is applied bitwise, or resulting in the combined flags as shown in Table 6.4. Table 6.4 SIGHASH types with their modifiers and their meanings. All ANYONECANPAY 0x81 signature applies to one inputs and all outputs. Non-ANYONECANPAY 0x82 signature applies to one input, none of the outputs. Single ANYONECANPAY 0x83 signature applies to one input and the output with the same index number. The way SIGHASH flags are applied during signing and verification is a copy of the transaction is made and certain fields within are truncated, set to 0 length and emptied. The resulting transaction is serialized. The SIGHASH flag is added to the end of the serialized transaction and the result is hashed. The hash itself is the message that is signed, depending on which SIGHASH flag is used. Different parts of the transaction are truncated. The resulting hash depends on different subsets of the data in the transaction. By including the SIGHASH as the last step before hashing, the signature commits the SIGHASH type as well, so it can't be changed, e.g. by a miner. In this example of Alice's transaction, we saw that the last part of the DER encoded signature was 01, which is the SIGHASH all flag. This locks the transaction data, so Alice's signature is committing the state of all inputs and outputs. This is the most common signature form. Let's look at some other SIGHASH types and how they can be used in practice. All ANYONECANPAY. This construction can be used to make a crowdfunding style transaction. Someone attempting to raise funds can construct a transaction with a single output. The single output pays the goal amount to the fundraiser. Such a transaction is obviously not valid and has no inputs. However, others can now amend it by adding an input of their own as a donation. They can sign their own input with all anyone can pay unless enough inputs are gathered to reach the value of the output. The transaction is invalid. Each donation is a pledge which cannot be collected by the fundraiser until the entire goal amount is raised. This construction can be used to create a bearer check or blank check of a specific amount. It commits to the input but allows the output locking script to be changed. Anyone can write their own Bitcoin address into the output locking script and redeem the transaction. However, the output value itself is locked by the signature. Anyone can pay. This construction can be used to build a dust collector. Users who have tiny UTXO in their wallets can spend these without the cost in fees exceeding the value of the dust. With this type of signature, the dust UTXO can be donated for anyone to aggregate and spend whenever they want. So I'm going to leave here to this video. If you like listening, please consider like, sharing and subscribing. Thank you.